Good morning and welcome to our fourth live broadcast lesson. Today I'm going to be talking with you about roots and squares. But before we do that, I want to say thank you to everybody who's been joining us so far. It's been really valuable. We've really enjoyed sharing the lessons with you guys, and we look forward to doing many more. Also, well done to our competition winners last week, Arushi and Ibrahim, who won our creative writing competition. There's another one ongoing at the moment, and if you want to find out more information, visit our social media pages or our website. To be in with a chance of winning your own £15 Amazon voucher. Okay. So on with today's lesson. Today we're going to be looking at squares. So first of all, I'd like you to think about what is a square number? What is a square number? Okay. Square numbers are numbers that you can arrange in a square pattern, and I'll show you what I mean. So a long time ago, people noticed that some of the numbers you could put, when you arrange them into an array, you could make them seem square. So you add the number 1, that fits neatly into one square here. You have the number 2 and 3 don't fit neatly into squares, but the number 4, 2, 3, 4, fits neatly into a square. If you notice the length of each side is 2 squares long. So this number is 2 squared. In other words, the root of this number 4 is 2. The root of this number 1 at the top is 1. 1 squared is 1, 2 squared is 4. The next square number, 3 squared. I wonder if you know what it is. You probably do. You probably can work it out. You've probably heard of these numbers before. Let me draw it on the board for you here. 3 squares down, 3 squares across will be our next square number. And that altogether is 9. There's 9 squares within it. So you're able to see that the square numbers increase. Now, a long time ago, people noticed this, and they noticed this pattern. Mathematicians throughout the ages have loved numbers that make interesting patterns. And this one was very interesting to lots of mathematicians. Leonardo da Vinci loved square numbers. Fibonacci loved square numbers, but they were discovered way before then. All the way back in prehistory, there's evidence of square numbers being used by different people. Okay, so what I'd like to show you is the next slide. Let's have a go. Okay, so on the board in front of you and on the slides, as you should probably be able to see on your screen, I've drawn out an array similar to this that I've written on my board. So 1 squared is the same as 1 times 1, and the answer of that number, that square number, is 1. The second square number, 2 squared, is 4. That's the same as 2 times 2. The next square number, 9, is the same as 3 times 3, and its root is 3, 3 squared. So we've got square numbers, 9, 4, 1, and their roots, 1, 2, and 3. Okay, the root is the number that has to be multiplied by itself to make the square number. Okay, so the root of 16 is 4, and the square of 4 is 16. The root of 25 is 5, correct? And the square of 5 is 25. But you know this already. What I'd like you to do first is to have a look at the square numbers that I've put on the slide. The squares of 1, 2, 3, 4 and 5. And I want you to work out the pattern. How much do the square numbers increase by each time? Okay. Is it the same amount each time? Or is it a different amount each time? And what do you notice about the numbers that the square numbers increase by each time? If you have any ideas, please put them in the comments on the video. Okay, we'll wait for a couple of comments to come in. If you need a bit more time to have a go at this question, then don't be afraid to pause the video. What do you notice about the pattern of numbers that the square numbers increase by? So we've got 1, 4, 9, 16, 25. The first 5 square numbers. What do you notice about the pattern of how they increase? Okay, so I'm going to work through it with you. From the first square number 1 to the second square number 4, we have an increase of 3. From the second square number to the third square number, we have an increase of 5. The third square number to the fourth square number, we have an increase of 7. Next, we have an increase of 9. I noticed something straight away about these numbers. They're the odd numbers. That will tell me straight away I can work out without having to do any multiplication what the next square number will be. I'm going to have to add 11 to get the next square number, 11 to 25, and that will give me the next square number of 36. Okay? 6 times 6 is 36, so I know that's the 6th square number. I can work out the next straight away. If I add 13 to 36, that will take me to 49. Okay, so there's a pattern to these square numbers as you move up. Now, I mentioned earlier that Leonardo da Vinci really loved square numbers. Now, he set a challenge to one of the kings in Italy at the time. And his challenge that he set was, can you find 2 square numbers that when you add them together, they make another square number? Can you find 2 square numbers that when you add them together, they make another square number? I'm going to ask you to write your answer in the comment section if you can. To let me know. Have a look, have a think about some of these square numbers. I'll leave them written on the board. We've got 1, 4, 9, 16, 25, 36, 49. Can you find 2 square numbers that when you add them together, they make another square number? Even better if you can find one that's not one of the ones I've got written on the board. Again, if you need a bit of time to work this out, feel free to pause the video. I'm going to let you know an easy answer now. One of the first ones that you can see, 2 square numbers that add together to make another square number. If you add 9 and 16, they make 25. So those are 2 square numbers you can see straight away, and there are lots of other ones too, other patterns that you can find throughout. Okay, and this was really interesting to lots of ancient mathematicians and mathematicians today, because these patterns that repeat help people to find out more in the world of maths. Let me give you another tip. We looked previously at the differences between the square numbers 3, 5, 7, 9, 11, 13, the differences that count up in the odd numbers. You can use these differences to help you work out what the square of a number is. So, for example, if we take 36, which is 6 squared, we know that. If you weren't able to work out what square number it was or whether it was a square number, you can work it out by subtracting the odd numbers in order. If we subtract 1, then 3, it gives us 35, 32, and subtract 5 as many times as you can until you get to 0. 20, it's going to give me 11, minus 11, that gives me 0, okay? And then I count 1, 2, 3, 4, 5, 6 odd numbers. I know that it's going to be 6 squared. And this works for every single square number. So if, for example, someone was asking you to check whether the number 169 was a square number, and you weren't sure, as a hint, it's 13 squared, you could work it out by counting back, subtracting back the odd numbers as you go. Okay, so a couple of hints and tips there. Now, at home you might be thinking, this is all well and good, but why is this useful? Well, for many mathematicians, physicists, people doing lots of jobs around the world, this being able to calculate squares and roots is useful for a whole range of things, from astronomy to sports to carpentry to more things. These skills and facts and patterns are cool on their own, but they also enable people to do cool things in their jobs. So today we're going to look at some quick tricks for calculating squares and square roots, not just the patterns, and then we're going to work out how we can apply it to the real world. Okay, so I'm going to move to the next slide. Okay, so the first trick I'm going to teach you is how to square any two-digit number. How do you square any two-digit number? Okay, now this is a trick that lots of mental mathematicians use. There are people called human calculators out there, and they use tricks like this to help them to square any two-digit number quickly and correctly in their head. Okay, to do it mentally. So I'll show you how it works. To do 18 squared, we could use the column method. But there's a speedier way that you can do it in your head. First thing you need to do is partition the number. 18 is 10 and 8. Now, we should be able to really quickly do 10 times 10 in our heads. That equals 100. We should be able to do quickly in our heads 8 times 8. That equals 64. And that's the first step. Do each partition number multiplied by itself. The last step that you need to do is to multiply each partition number by each other and then double it. So the next step is to do 10 times by 8 times by 2. 10 times 8 is 80. 80 times 2 is 160. Last step, add all of those up. 4, 2, carry the 1, and 3. 18 squared is 324. And if you were to calculate it on a calculator, it would give you exactly the same answer. Okay, let's do a second example. Let's work with some trickier numbers here. I'm going to go with 83. 83 squared. Okay, so first step, we need to partition the numbers. 80 and 3. Work this out with me at home. Then what you need to do is each of the numbers multiplied by themselves. Well, 3 times 3 is easy. 3 times by 3 is 9. 80 times by 80, well, that sounds a bit trickier. But I know 8 times 8 is 64. And each of the 80s has a 0 on the end. So I'm going to make sure I put them in as placeholders at the end here. 6,400. Then I'm going to do 80 times by 3 and double it. 80 times 3 times 2. Well, 80 times by 3 is going to be, or 8 times 3 is 24, just a 0, 240. And then double it, 480. And if I add these together now, 9, 8, 8, and 6. 83 squared, 6, 8, 8, 9. Okay, these tricks work and people use them as mental maths tricks. You can keep these numbers, it's only 3 numbers you have to keep in your head. And mental mathematicians who work quickly do these in their heads. For now, you can work it out on paper. So I'm going to give you a minute or so to try and work out the 4 questions on the board. Instead of the 83 squared that's there, can you work out, for number 3, can you work out 79 squared? So I'm going to give you a minute to work through those 4 questions on the board. Remember the steps. First, partition. Second, multiply each by itself. We've got 30 seconds left. Third, multiply each digit together. And double, and then lastly add. Okay. If you need more time to work those questions out, pause the video now and join us in a moment. We'll go through the answers now. Okay, so the first question on your board is 26 squared. 26 squared. So I'm going to go through this pretty rapidly. We're going to partition into 20 and 6. 20 times by 20 is 4, and then 2 zeros as placeholders, 400. 6 times by 6, 36. 20 times by 6 is 120, doubled, 240. Add those together. We've got 6, 7, 6. 676 is 26 squared. Question 2. We've got 54 squared on the board there. 54 squared, partition, 54. 50 times by 50 is 25, 5 times 5 is 25, plus the 2 placeholders, 2,500. 4 times by 4 is 16. 50 times by 4 is 200, doubled is 400. Add those together and we get 2,916. That's 54 squared. The next one I asked you to do, instead of doing 83 squared, because I used that as an example, we're going to do 79 squared. 79 squared. Okay, partitioned, it's 70 and 9. 70 times by 70, or 7 sevens are 49, plus the 2 placeholders, 4,900. 9 times 9 is 81. 70 times 9 is 63, plus the placeholder, 630. Add them together and we get 5,611. Okay. Last one we're going to do is 17 squared. 17 partitioned is 10 and 7. 10 times by 10 is 100. 7 times by 7 is 49. 10 times by 7 is 140, doubled, 280. We're going to add them up. 1 and 4, 429. Well done to those of you who got all of those correct. No worries if you didn't, you can try again at home. Have another practice at using the method and make sure that all of your multiplications were correct. Okay, so that's a quick method for squaring any two-digit number, and it works for any two-digit number. Okay, moving on, we're going to look at square rooting any number. Now, square rooting is really hard. Squaring is easy, you're multiplying a number by itself. But to square root, you've got to work out what number times by itself makes an answer. Now, this works if you know your squares. For example, if you know your times tables up to 12, you'll know that, for example, 121 is 11 squared. To write that differently, the square root of 121 is 11. Okay, so it's the opposite way around. 11 squared is 121. The square root of 121 is 11. For another number, let's go with 64. Okay, 64 is 8 squared. The square root of 64 is 8. So it's just writing the same information the other way around. And those of you who know your times tables up to 12 will know these quite quickly. But it gets a bit trickier if someone asks you not to work with a number that squares straight away. For example, 132, which is on the board, is not 11 times 11, that's 121. It's not 12 times by 12, that's 144. So what is it? That's really hard to work out, and many mathematicians struggle. In fact, it's an irrational number, which means it goes on forever. But there's a mental way, and I'm going to show you it now, to do a quick estimate. What you need to do is find the nearest square beneath it. So 11 squared is 121. That's the nearest square beneath 132. So the answer is going to be 11 point something, 11 and a fraction. Next, what you need to do is work out the difference between 11 squared and the number that you're trying to find the square root of. 121, 132, the difference between the two here is 11. And the last step, the last thing that you need to do is double the answer that's there, and that will give you your denominator. So the answer is 11 and 11/22, which is the same as, divide the top and bottom by 11, 11 and a half. So our answer to the square root of 132 is approximately 11 and a half. If I work out on a calculator exactly what the square root is, square root of 132 is 11.48912529307307, etc, etc, etc. And it goes on and on for a while. So our estimate of 11 and a half is a really good and clear estimate of the numbers that it will work out as, and we can do it quickly and mentally. Let's try another example to help you practice. Square root of 76. Okay, doesn't go exactly as a square, it's not a perfect square. So let's think about the nearest square beneath it. Okay, the nearest square beneath 76 is going to be 8 squared, which is 64, because 9 squared is 81, so that's too big. Okay, so our answer is going to be 8 and a fraction, 8 point something. Now what goes on the top of the fraction? The difference between 8 squared and the number that we're finding the square root of. Difference between 64 and 76 is 12. Last step, to get the denominator, double the number here. 8 and 12/16. That gives us the same as 8 and 3/4. So our answer is going to be approximately 8.75. On a calculator, I'm going to work it out. The square root of 76 is 8.717797, etc., etc. So that's a close enough estimate for square rooting, making these answers as fractions. I'm going to ask you now, let's do the first one together, the square root of 26, and then I'm going to ask you to do the remaining 3. So square root of 26, well, I know straight away 5 squared is 25. So the answer is going to be 5 and something. 5 and some sort of fraction. On the top of the fraction goes the difference between 5 squared and the number that I'm finding the square root of. The difference is 1. On the bottom of the fraction goes double the number just here, 1/10. So the answer is 5 and 1/10, approximately 5.1. Okay, I'm going to give you a minute now to have a go at the remaining 3 questions just there. Okay, so steps are, you can carry on while I'm talking about the steps. Steps are, firstly, find nearest square beneath. Secondly, find difference. Thirdly, double for denominator. Okay, those 3 steps will help you quickly estimate any square root, and that works up to any number as long as you know the square that you're working with. Okay, if you need some more time to work out these questions, please pause the video now. Let's have a look at question 2. Question 2 asks you for the square root of 40. Square root of 40. Okay, so the nearest square, we need to find that first, is 6 squared, 36. So the answer is going to be 6 and something. Numerator is going to be the difference. 6, the difference is 4. Denominator is going to be double this number, 6 and 4/12, which is the same as 6 and 1/3. Well done if you got that correct. Let's have a look at the next one. 83. Find the square root of 83. I know my times tables, so I know that 9 squared is 81, and that's our closest square number. Then I'm going to find the difference. Okay. Once you've found the difference between, sorry, I need to write this down, so we know the answer is going to be 9 and something. The difference is 2. On the bottom, we double the squared number that we found. Okay? So the answer is going to be 9, when we simplify it, and 1/9. Well done if you got that answer. The last question. Okay, square root of 17. I know that 4 squared is 16, and that's our closest square. Okay? So the answer is going to be 4 and something. The something is the difference between 17 and 16. And then the denominator is the doubling of that first number. So the answer is going to be 4 and 1/8. Okay? Now remember, these aren't exact, they're all approximations, but they're really good approximations to use when you're trying to work out a square root. It's something very tricky to do. It's something that many high school students and even adults wouldn't be able to do or struggle with. So I'm giving you a really cool head start to be able to start doing some of these square roots and impress maths teachers in the future and apply some of these skills. Now, I've shown you how to do squaring and square rooting, some good quick methods for that. What we need to do next is have a think about how we're going to apply square rooting and squaring numbers. So first of all, on the screen just there, I'm going to talk to you about one application that there is. In the car industry, it's really important that the cars that they sell to people are safe and easily usable for all of the drivers and the people that go into cars. So people spend a lot of time working out how much energy a car has when it crashes, and whether the seat belts, the crumple zones in the car, the airbags, those sorts of safety features will be able to protect the people inside the car at different speeds. They even do some really cool experiments with crash test dummies, and you might have seen some of these things, where they drive cars into brick walls using some mannequins in the cars and see what happens. But here on the board is an equation that they use to work out how much energy a car has and whether their safety equipment is going to work. Okay, so the equation is energy is half of the mass times the speed squared. It says it there on the board. Energy is half times the mass times the speed squared. Okay, so what we need to do is work out exactly how. Let me rewrite that equation. Energy equals half times the mass times the speed squared. Okay, so the car safety features in this car, in this example, can protect the driver from 200,000 joules of crash energy. Okay, so will the driver be protected? Let's look at some different speeds. I'll work through the first one with you. So 1 meters per second, this car is going really slowly. It's like it's just started driving in a driveway. It's maybe reversing or parking. We think probably at this speed, the seatbelt will be able to protect the driver, but let's check. So we know that the mass of the car, and I'll let you know that now, the mass of the car is 1,200 kilograms. It's the same in all of these experiments. This car weighs 1,200 kilograms. Okay, so we need to do half times by 1,200, and then we need to multiply that by the speed, which is 1 squared. Half of 1,200 equals 600. The speed is 1, 1 squared is 1, and then 600 times by 1 is 600. So the energy in that crash is 600 joules. The car safety features can protect us from 200,000 joules, so I think the driver will be safe in this instance. Let's have a look at the second instance. The car weighs the same. We need to multiply that 600 by the speed squared. Well, the speed this time is 5 meters per second. This is a bit faster. This is like a car going down a slow street. It's maybe just going down towards the end of your road, a road of speed bumps, not going very fast at all. 5 meters per second. So we're going to do 5 squared, which equals 25. And then we're going to multiply that by 600. Okay, and you can use your column method to do that. 25 times 600. 5 times by 600 is going to give us 3,000. 20 times by 600 is going to give us 12,000. Add them together, we get 15,000 joules. I'm going to write that neatly here, 15,000 joules. Okay, that energy, as expected, is enough to be protected by the safety features of the car. Okay, going down a slow road. What about the next three? I'm going to give you a minute or so to work out the next three. Will the car driver be protected in each of those instances? Remember, the car always weighs 1,200 kilograms. For reference, 11 meters per second is like going about 30 miles an hour down a normal side street. 23 meters per second is going pretty fast now. It's maybe going down a fast road, a dual carriageway. And 36 meters per second is going really fast on the motorway, probably too fast. What do we think? If the car crashed, stopped straight away, would the safety features be able to protect the drivers in those instances? You might need to use our quick method of working out square numbers to be able to solve these problems. And I just want to point out that this equation works out the energy of the car if it stopped straight away. In most real life crashes, the car doesn't stop straight away. It would slow down a little bit quicker, a little bit slower than that. So in most cases, the safety features will still work. Let's have a look. 11 meters per second. So 1,200, we need to half it again. Half times by the mass. That's 600. And then we need to times it by the speed squared. 11 squared is 121. So we need to do 600 times by 121. 600 times by 1 is 600. 600 times by 20 is 12,000. And then 600 times by 100 is 60,000. Add them all together, we get 72,600 joules of energy if they're going at 11 meters per second. Okay, that's starting to get a bit more dangerous, but still not really testing. This is the speed on a normal road. Still be protected if you were to stop straight away in a crash. Let's have a look at the next one, 23 meters per second. So we need to do 600 times by 23 squared. Gonna have to use our quick method. 23 squared, partition it. 20 times 20, 400. 3 times 3 is 9. 20 times 3 and doubled. 60 doubled is 120. Add those together, that gives us 529. That's 23 squared. 529 times by 600. Ooh, this is getting quite big now. I'm assuming that this crash on a dual carriageway might start to get a bit dangerous. 9 times by 600. Well, that's going to give us, apologies there, 9 times by 600. That's going to give us 5,400. 20 times by 600. That's going to give us 12,000. 500 times by 600. Well, let's add in the zeros first. And 5 times by 6 is 30. So the energy for this one, 317,400 joules. So it looks like if you're going quickly on a dual carriageway and you crashed instantly, then this car's safety features wouldn't protect the driver. Let's have a look at the last one, 36 meters per second. I think we can safely assume that it's not going to protect the driver because this one didn't. But let's have a look how much energy there is in this crash. So we've done half times the mass already. That gives us 600. Then we need to do 36 squared and multiply it to work out the answer. Our quick method for squaring. 30 times by 30, that's going to give us 900. 6 times by 6 is 36. 30 times by 6, 180 doubled, 360. Add them together and we will get 1,296. Okay, that's 36 squared. 1296. Then we need to do 600 times by 1,296. This is going to be huge. 6 times by 600 is 3,600. 90 times by 600, put the zeros in first, it's going to be 54,000. 200 times by 600 is going to be 120,000, and 1,000 times by 600 is going to be 600,000. Okay, add these together, we're going to get 777,600 joules of crash energy. That is a lot, and in this instance, in an instant crash, it seems that the seatbelt wouldn't be able to protect the driver. Just going to say again, in real life crashes, the seatbelt would be able to. They're much more protected. And there's many people that work on these problems so that they can calculate how to make you safe in all crashes that you need to, especially if you're following the speed limit. We have some more real life situations next. So that's one. You can use these square numbers to work out the energy of things in a crash. You can use them for lots of other things too. Another instance when it might be used is for carpenters. So carpenters often have to, and builders often have to make sure that a room is square. And when I say square, I don't mean that it's the shape of a square. I mean that all of the angles in it are 90 degrees. All of the corners are 90 degrees. Because most buildings need to be the shape rectangular or square so that they can stand up. And when builders build them, an easy way to measure it is using a maths trick. Some of you might have seen this maths trick before. It was invented by a clever mathematician called Pythagoras, and it's called Pythagoras' theorem. Okay? This maths trick helps you work out the long side of a right-angled triangle. So if I draw on here, we've got our triangle with a right angle. This maths trick helps you work out the long side of that right-angled triangle. Why is this useful? Well, for a builder, if they're building a rectangular room, let's draw that neatly. Builder making a rectangular room, where a corner is 90 degrees, they can check that it's square if they can work out the length of that diagonal line, because you can see that it's made up of two right-angled triangles. There's one at the top here, one at the bottom here. Okay? And the trick is this. A squared plus B squared equals C squared. The long side is C squared. A squared plus B squared equals C squared. Okay? We've only got time to do one of these questions. You can do the rest after the lesson. And the question we're going to do is the one lower. Is the room square? A squared plus B squared equals C squared. Okay, is the room square? Now, if it's square, then A squared, 45, plus 45 squared, plus B squared, 28 squared, will equal 53 squared. Okay, so let's check that now. I'm going to write these numbers in here. A equals 45, B equals 28, and C, this long diagonal side, is 53. So if the builder had measured these 45 centimetres, 28 centimetres, 53 centimetres, he'd be able to check that his room was perfect with all of the angles at 90 degrees if all of these worked out correct, and when they added A squared plus B squared, it equals to C squared. So let's work out what A squared is. 45 squared, well, we can use our trick. 40 and 5, 40 times by 40 is going to be 1,600. 600. 5 times by 5 is 25. 40 times by 5 and doubled is 400. Okay, add those all up, you get 2025. 45 squared. 28 squared. We need to do 20 times by 20, which is 400. 8 times by 8, 64. 20 times by 8, which is 160, and doubled, which is 320. Add them all together, that's going to give us 784. Okay, the last one, 53 squared. 53 squared. 50 times by 50 is 2,500. 3 times by 3 is 9. 50 times by 3 is 150 doubled, 300. 2,809. So, if this is correct, a squared plus b squared should equal c squared. Let's check. 2025 plus 784. 9. Carry the 1. 8, 2, 2,809. So the builder's room is square. Using a quick maths trick, they can quickly work out whether their room has perfect angles, because it's really difficult to measure the angles in a corner of a room. You can't use a protractor. Okay, that's it for today. Please complete the rest of the questions after the lesson. There's a couple above that we just had to miss out. And tune into our webpage, our OxBridge UK activities, home learning webpage, to help you with any other tasks you want to do at home. We've got bundles of free resources there. We have our creative writing competition, which is available and open to all, and you can win a £15 Amazon voucher for taking part. And we have oodles of other free things there for you to do at home. Have a great week, and we will see you next time. That's bye from me.